if we go back to chapter 1, we studied the general idea of what differential equations are and how they fit into the big scheme of things. And one of the important things to be able to do in this class is to look at a differential equation and identify what kind of differential equation that is. So we talked about the order of the differential equation. We talked about whether it's linear or not, and a few other things. And now in chapter 2, we focused on first order differential equation. And within this big group of first order differential equations, we took a look at how to solve for these differential equations by classifying them into these categories. And that's what the quiz was all about. And so the quiz was all about looking at a differential equation, figuring out what kind of differential equation that is so that you can solve for it. And so we want to try to be able to solve for it based on a handful of techniques that we have. But if you're looking at a differential equation, you have to know what technique to use. Somewhere in the middle of chapter 1, they decided to include modeling where you set up the differential equation. But since in chapter 1 we didn't know how to solve for these differential equations yet, they just set them up and say that's all we're going to do with them. So now that we know how to solve a bunch of differential equations, specifically the first order differential equations, in this new chapter, chapter 3, we're going to try to reset them up as per your homework in chapter 1, somewhere in there, 1.6 or something, and then actually solve for them this time instead of just setting them up. So this first one is not really anything to talk about because we already know this problem pretty well. And the only thing that maybe we can mention is the fact that it's a growth, it's a decay, it's a half-life, carbon dating. That type of problem comes back to this type of differential equation, which is something that you probably saw back in Calc 2. But this is an example of a separable differential equation. It also happens to be a first order linear differential equation. So we're not going to do too much with this, aside from look at it and say, been there, done that. Now let's go on to a slightly more interesting, not much more interesting, but a slightly more interesting problem, and that's Newton's law of cooling, which you should have seen back in 1.6. We had a couple of problems that are similar to this, I think. And remember, back then all we did was set it up, but now we're actually going to try to solve for this. So Newton's law of cooling / warming says that the rate at which temperature of a body changes is proportional to the difference between the actual body that you're measuring and the surroundings. And the surrounding temperature is sometimes called the ambient temperature. So let's say capital T represents the temperature of a body. By a body, that just means, I mean, it could actually be a body, or it could be like a cake in the oven, or coffee that you just poured and now it's sitting there getting cold. So a body, T is the temperature of a body at time little t, and then Tm is the temperature of the surrounding. Then capital T dt dt, capital D, or d capital T d little t is the rate at which the temperature of the body changes. And Newton's law of cooling, I guess this is law of cooling / warming, translates to this thing. It's proportional, so there's a constant of proportionality. Say dt dt is equal to some constant times the difference of the body, the temperature of the body and the temperature of the surroundings. So here's an example that I dug up in your textbook, or at least the old edition of your textbook. And let's try to do this problem. So the rate in which the body cools also depends on the exposed surface. Oh, so this one includes something else. This one doesn't just include the coffee, it includes the cup also. So it's a little bit more complicated than the general law of cooling. So let's do this example. A rate at which the body cools also depends on its exposed surface, S. If S is a constant, then the modification for the differential equation is going to be dt equals a constant times S. That's just another constant times T minus Tm. Where the constant of proportionality K is less than 0 because it's cooling. So we expect the temperature to be going down. And Tm is also constant. That's a surrounding. Suppose that two cups A and B are filled with coffee at the same time. Initially, the temperature of the coffee is 150 degrees Fahrenheit. The exposed surface area of the coffee in cup B is twice the surface area of the coffee in cup A. So after 30 minutes, the temperature of the coffee in cup A is 100 degrees Fahrenheit. So if the temperature, the ambient temperature in the surroundings is 70 degrees, then what is the temperature of the cup of coffee in cup B after 30 minutes? Okay, so how can we imagine this? What's going on here? We got two cups. So we'll have two differential equations, and the difference between them is just one cup will have twice the surface area. So cup B is going to have twice the surface area of the coffee. What does that mean? How can we picture that? Bigger cup, right? So the exposed area. So imagine you have cup A and then cup B. So you got coffee coming out. This is a surface area that's exposed. This is a surface area that's exposed. So the surface area for cup B has twice the surface area that's exposed in the ambient temperature. Right? So how would we solve for this? So we probably want to know what's happening with cup A, right? Should we? Find out what's happening with cup A. So dt equals ks t over tm. Is there anything we know at this point? Let's see, what do we know about cup A? So after 30 minutes, we have a temperature that's 100 degrees. So for cup A, temperature, I'm going to put a little sub A here to say that we're dealing with cup A. The temperature in 30 minutes is equal to 100 degrees Fahrenheit. Is there anything else we know? The what? TM? What's TM? Well, it would also be the same for cup A, I think. And yeah, so it's part of TA, and it's also the same because we're pouring these two cups on this in the same kitchen where they have the same temperature. T what? So T A of 0 is 150 degrees, which also happens to be the same for the other one. It's also 150 degrees. Okay. So I think I don't know if we saw this being solved for, but now that we have the tools for solving first order differential equations, we should be able to solve for this. Assuming that K and S and Tm are all constants, how would we solve for this differential equation? Let's solve for this differential equation in general for now. Let's solve for this differential equation using what? It's first order. So we have, is it linear? Is it separable? Is it exact? Is it integrating factor? Is it linear? Pretend it's the quiz and it's linear. All right. So let me tell you that if you had a choice, and when you're looking at a first order differential equation, the first thing you should try to do is ask yourself if it's separable. Now, we didn't have any separables in the quiz, but that's the first thing you should do, because that's like when you're integrating back in Calc 2, the first thing you ask is that, can I do a U substitution? Because that's the easiest thing I can think of, right? So you ask yourself, is it separable? Because that's the easiest sort of technique. That's the first one we learned, I think, in 2.3 or something. So ask yourself, if it's separable. And if it's not separable, then you run through the list. Okay, first order linear, exact, and whatever else. So is it separable? Yeah, yeah. In fact, what are the two variables? T and T, capital T and lowercase t, right? Do we see any lowercase t here? So we don't even see a lowercase t. So we can take the stuff with a capital T and move that over to the capital T dt, d capital T, and then move everything else little t. In fact, if you don't have your independent variable at all in the differential equation, what's that called? 2.1, what? Autonomous. It's an autonomous differential equation, right? So an autonomous differential equation is separable because there's no independent variable there. Just bring all the dependent variable stuff with a D capital T, with the dependent side. And then if you have any constants, now Tm is a constant, but it's stuck with a T. So if I were going to separate this, it should look like this. So that's the whole left side. And again, the Tm is attached to the T in the way that you can't break it up when you're multiplying or dividing. It's not a factor. And then the rest of them are constants. The K and the S are constants. And so they can just hang out with a little t. And then when you integrate, then the stuff is going to follow through there. Okay? All right. So now that we do know how to solve for this, we just integrate. And remember that Tm is a constant. So I don't know, in your head, do this U substitution, and then you'll be in ln. And then there's no extra factors coming out. So it's just going to be the ln of t minus Tm. And if we look at the Tm is 70 degrees and little t, or the capital T, is the temperature of the coffee, we're assuming that if you're in a room that's 70 degrees Fahrenheit, your coffee is not going to get any colder than that. So we can probably assume that this is always going to be positive. So we can decide to keep the absolute value or not. It's up to you. And then we have Ks little t plus your constant. Don't forget your constant. And then we want to generally you want to solve for capital T, the dependent variable. So we'll take E of both sides and then we'll solve for T. So E to the K S T, E to the C is a constant. We can call that T sub 0, which is 150 degrees. And then this Tm, after we took the E to both sides, we have to bring that back over to the other side. So that should be your temperature function, generally. Okay? So if we put 0 in there, actually T of 0 is not 150. We have to take into account the Tm. So let's work with cup A. With cup A, I got Tm is equal to 70. And then we'll put in the initial condition that says when little t is equal to 0, capital T is equal to 150. So really, it doesn't matter what K is or S is. That's going to disappear. And then, so this is just equal to 1. And then, so T sub 0 is equal to what? It's what? 80? Right? And so now we have T of T 80 e to the K S T plus 70. All right. So S, they don't give us much information about the surface area that's exposed. All they said was for the second one, it's twice as much that's exposed. And so what we want to do is we want to possibly solve for K. And the way we can solve for K is this piece of information to see what happens in 30 minutes. And so we'll use that piece of information to solve for K. That says that when little t is equal to 30, then capital T is equal to 100. And so we could solve for K maybe. I can do some other stuff here. But let's see if we could solve for K. Subtract 70, divide by 80, so that's 3/8 on the other side. And then I think at this point, let's just try to solve for K. We have to take the ln of both sides. So I can keep going down here. Yeah. So ln of 3/8 equals 30 ks. And so I'm interested in looking for K. K is equal to 1 over 30s 3/8. This is an S, not a 5. But we don't know yet, but we know that for cup A is S, cup B will have 2S because it's twice the surface. We're looking for the temperature of cup B, which means we have to translate everything to cup B. And the way we're going to do that is just, instead of S, we'll use 2S. All right, so we come back and rewrite our d of t is equal to 80, this whole thing. Ooh. Decimal? Um, yeah, that's probably a better thing to do. Oh, there's an extra s in there, right? S times t. Yeah, we can cancel the s's. All right. So we got this information here about the cup A. Now we want to figure out what happens in cup B. In cup B, well, I was going to say we can probably use this formula to figure out what happens, but your cup B has twice the surface area, so I think we just need to double the surface area. Instead of having S, we'll have 2S. So let me see if I can do this real quick. For cup B, we'll essentially have the same thing. So 80 e to the k, that's 1 over 30. And I'll keep the S here because your cup B is going to have twice the surface area. Hmm? No, because, well, the S that we solved for here came from cup A. And so we're using that information to help us figure out what happens in cup B. And so this is the cup A business that we were able to solve for. And then the difference between that and this cup is that this is twice S. If you imagine putting 2S here, then the 2S is cancel and they'll be the same answer. So we want to know for cup B, we'll put 30 in there. And so 80 e to the 1 over 30 S ln 3/8, 2s. The s's will cancel, and then this will have an extra 2, plus 70. So the thing to do is to compare what happens in cup A and cup B by putting these values into your calculator. Oh, on 30 minutes, the cup A is supposed to be 100 degrees. If you have a bigger surface area, do you think this would be cooler or warmer than 100 degrees? This should be cooler. So expect this to be less than 100, and hopefully it is, because if it's not, then we did something wrong. Okay? All right, we have a lot more examples to go through, so we'll do that on Thursday, and we have an actual exam a week from Thursday. So the exam will cover chapters 1, 2, and 3. All right, so if you want to start studying, now's the time.